So in our extra credit question, which of the reactions is not predicted to produce products? Anybody happen to look it up, figure it out? Out of curiosity. Did I actually say? No. I said 3 and 4 are likely to relatively the same as each other, and they're going to produce less products or less efficiency than 1 and 2. But I didn't say which one would not work. Number 4 does not work at all, period. You get no products out of number 4. Okay. What type of reaction is happening in number 4? What we were doing is putting on a CH3, also known as an alkyl group. So we're doing an alkylation. What type of alkylation? We're using the aluminum trichloride. We've got a Friedel-Crafts alkylation. The Friedel-Crafts alkylation, if you remember back to the slides where we talked about it, I said you needed to have an active ring or an active nucleophile. The nucleophiles in both 3 and 4, those aromatic rings, are deactivated. And as we were alluding to, it's because the electron density can move out of the ring. Okay. When we look at a Friedel-Crafts alkylation, we form a carbocation. That carbocation is not particularly stable, so we need a really strong nucleophile to react with it. So it has to be an activated one. In case 4, that is a deactivated nucleophile, not going to react under Friedel-Crafts conditions, which we'll talk about again in just a little bit, because I think I have another slide on it. So our lesson that we kind of picked up out of that is that we can look at the atoms attached to the ring and see how those atoms affect the overall position of our reactivity of the ring, where the nucleophilic sites are, and potentially change something about the activity of it. So for instance, if we take a look at atom X in that top case, let's see, do I actually have it on the slide? Atom X has more electrons. Okay. We know it has more electrons because we can see the lone pair. Okay, so in this case, I picked one that's relatively obvious. That lone pair can donate down via resonance. And if we draw out our resonance structures, you will end up seeing that we can put a negative charge on the ring at the ortho and para positions. Okay, all ortho and all para. I'm just going to do kind of a dotted line to sort of represent that. Okay. If I have negative charge at those positions are now what? Nucleophilic. And in comparison to, say, our straight normal benzene, where we had just a hydrogen, okay, they are more nucleophilic than we started with. Because we've now made it more reactive or more nucleophilic, we can refer to atom X as an activator. Because what it will do is speed up the EAS reaction. Okay. Not only will we refer to it as an activator, but we're also going to look at where that species would react. Under EAS conditions, with atom X in this case, we've got negative charge at the ortho and para positions. Well, in an EAS mechanism, we need negative charge. Those positions are now more nucleophilic. We would expect the substitution from our EAS to occur at those particular positions first. Okay. So we can refer to it as a para-ortho director. And I don't know why I just wrote that out, because it's already typed there. Okay. But let's just pretend it wasn't. Okay. You'll notice that when most people talk about EAS reactions and activators in particular, you'll almost always hear them refer to it as ortho-para. And you will probably hear me say the same thing, ortho-para favoring. I'm really trying my best to push para-ortho as far as the ordering in that statement. It doesn't sound quite as nice. At least I don't think it sounds quite as nice. But it is more important to explaining the reactivity. We have 2 sites of reactivity. with an activated ring. We have the ortho and the para positions. Well, which one comes out and wins first? Where should I, given the opportunity to do a single substitution, where should I do that substitution? At the ortho or para positions. Okay. Now we run into a question of why should it be at the para?
Because there's less electron density.
If there's less electron density at the para position, it's not going to react. It doesn't have electrons.
Less, not electron density, it's less steric.
Sort of the right idea. It's a steric hindrance argument. Atom X, and this is very kind of hand-wavy to do, but it kind of works. Atom X is a bunch of electrons. The very first step in our EAS mechanism is that we take the electrons from our double bond. We're going to use our ortho position. We take those electrons and we move them out of the ring. What do they then go right next to? Electrons. What happens when electrons get near electrons? They repel and they cycle back down to reform the pi bond. If we instead look at the para substitution, at that double bond, if it comes out, what is it going by? Hydrogen, which comparative to our X atom has less electrons. There's less steric hindrance to prevent that reaction from occurring. So we would expect the para to be favored over the ortho. Can we push it further so that we favor the para even further or more? And how might we do that? We can make atom X even bigger. Okay? And it may not necessarily be the atom, but the things attached to atom X. The bulkier that group is, the less likely we'll see the ortho substitution, the more likely we'll see the para substitution. Okay? Hence the reference of para-ortho. If we're sticking with a relatively small atom X, say like NOH, we would expect a relatively higher proportion of our ortho substituent to come into play. But we're still looking at a favoring of our para. You're probably seeing something on the order of 55% para, 45% ortho. There is still a steric hindering effect at that position. Kind of make sense? What happens when we move to atom X having a positive charge? Well, just like we did with atom X having extra electrons, we want to see is there a resonance effect. And we can draw a resonance system where we have electron density come out of the ring to stabilize that partial positive. The result is that we put a charge on our ortho position. What charge builds on that position? A positive charge. Okay. I'm going to take a quick minute here. Positive charges. I have noticed that a lot of students have been missing drawing the positive charge. This is kind of class-wide. If you've removed electrons or moved electrons from any position, you should be evaluating charge. Okay. If it started negative and it loses electrons, fine. Okay, it can go neutral. But if it starts neutral and you move electrons away from an atom, it had better be shifting to being a positive. Okay, because it's lost electrons. Do not lose those charges. They are of critical importance to understanding where your chemistry is going to occur next. If we continue to draw our resonance structures, you should notice that you'll be able to put a positive charge at the para and also at the other ortho position. So atom X has withdrawn electron density from the ring. If we now look again at our EAS mechanism, trying to decide, should this reaction work? Well, what happened to our ring? Is it more nucleophilic or less nucleophilic? Less nucleophilic. The word that we use to describe its now weaker ability to react is that it is a deactivated ring. Atom X, in this case, is a deactivator. It's going to slow the reaction. If we say, okay, let's give it enough energy so that it does still occur, where would I expect that substitution to happen? Well, in the case of our EAS mechanism, our ring must act as a nucleophile. It must act as an electron source. The ortho and para positions have how many electrons? Worse than none. It's like negative electrons because they are formally positive. If they are missing electrons, can they act as a nucleophile? No. Which means the ortho and para don't exist as a possible product. The only thing we've got left is the meta position. Is it negatively charged? No. So should it react fast at that position? No. But is it reacting faster than the ortho and para positions? Yes. Okay, that is why that structure is referred to as a deactivator or a deactivated ring. You'll typically see directors following after this. Atom X, if it has less electrons, is a meta-director. Atom X, if it has more electrons, is a para-ortho director. In the text that's already written up there, we've added some more information to it, so maybe you'll catch on with this question quickly. You'll notice that when I've been saying it, atom X has more electrons, or atom X has less electrons. Well, more and less electrons than what? We have to have a baseline to establish what we're looking at more and less from. That baseline is hydrogen. Why hydrogen?
That's what's most prevalent. Randomly.
What is the difference between our top structure, our bottom structure, and everything we've been talking about so far with EAS? This one. What changed? Atom X replaced hydrogen. Hydrogen is our baseline because that is our standard form for our structure. If we have more electrons than hydrogen, we are now an activator. Well, what atoms have more electrons than hydrogen? All of them have more electrons than hydrogen. Okay? Hydrogen has the fewest amount of electrons in our periodic table, so every atom has more electrons than hydrogen. This brings up an interesting dilemma. If every atom has more electrons than hydrogen, how do I ever put an atom on there that has less electrons than hydrogen? I can put an atom on that builds a positive charge, okay? Either partial or formal. Okay? So your directing or your activator groups are usually easier to recognize because they have lone pairs, but they don't always have a lone pair. The deactivators are easier to recognize because they almost always carry a positive charge. Okay? Or in a resonance structure can show a positive charge. Okay? Should we look at a couple quick examples? I have to erase the middle of this. Activated or deactivated? Feel free to shout it out when you know. Activated, right? Why? Carbon has more electrons than hydrogen. Really? No, it's deactivated. Okay? Because that oxygen can withdraw electron density from the carbon. Okay, through a resonance structure. Is there a resonance structure to show that that carbon carries a positive charge? No, so this is a little weird. Okay, it is deactivated. Why is it deactivated? The fluorines are electronegative enough that they will withdraw enough electron density from the carbon that it does start to carry an effective partial positive. Okay. That is now a deactivated ring. Can we show a formal resonance structure to show that it's deactivated? No, because I can't even take electrons out to share with it formally because that would oversaturate the carbon. okay, or over, not saturate, overfill the carbon with electrons, exceed its octet.
Would that only happen if you had 3 fluorines, or would you get that with the other, some other halogens attached to them?
And this is where you would run into a gray area, as you would shift from being probably still an activator to starting to become less and less active until it eventually switched to a full-on deactivator. When we're looking at this substituent, or this particular pattern, the CF3, that is one of your classic examples of a deactivator. Very rarely do you see one halogen attached to it. Okay? For that very reason, it's kind of a gray area. Okay? Other questions? Okay. So this next, go ahead.
If it's just a CH3 group attached to it, would that be an activator then?
That is still an activator. There is nothing drawing electron density away from that carbon. If anything, the carbon's actually sucking electrons from the hydrogens that it's attached to, because carbon is more electronegative than hydrogen, just not by much. Okay. And the system seems to, I think we're okay. So what we've got here are actually all of the resonance structures so that you can see each of those individual contributors and what ends up happening within it. Okay. So all we're trying to do is, once we have a ring with something attached to it, identify that atom attached and see what happens. Where does it best classify? Okay. Some potentially trickier options here. Activator, deactivator. Okay. Atom X is what? That carbon, which technically has more electrons than hydrogen. We do have an electron withdrawing group further out there, but we want to keep our focus on the atom attached to the ring. The atom attached to the ring has more electrons than hydrogen, albeit it's starting to lose some of them. So it's not a super strong activator, but it is still an activator. Okay? So don't just look for, oh, there's a positive charge out there. Look for the atom attached to the ring. Whoops, that was not what I meant to do. Here's a fun question. I always like asking this question on exams. And you guys don't even have to worry about it this time around. At least from my exam. It may show up on the final. EAS reaction, let's say BR2. We'll even add the catalyst. An important question was brought up today in office hours. Do you need to have the catalyst? No. Okay. The catalyst we initially showed as being present because what we were reacting was a benzene, or just benzene, no substitution on it. It's not activated, it's not deactivated. We tend to need a catalyst to initiate and get that reaction to go. Once we have a substituted benzene, we might be able to get away without the catalyst because that substitution may make the benzene more active. Okay? So just because you don't see a catalyst doesn't mean it's not going to form an EAS reaction. Okay? Be aware of that. So, want to do a bromination with this? Where does it substitute? And in fact, I'll even give you one more clue. One position. Actually, I'll even give you two positions. Two positions. Brominate this structure twice. Okay. Spend a minute. We'll go ahead and start. Which ring do you want to look at first, left or right? Okay, left ring. So we're going to look at the left ring. We need to look at atom X. Where's atom X? So that's CH2. Does CH2 have more electrons or less electrons than hydrogen? More electrons. So what is it doing effectively? It is sharing electrons with our structure. I know that's not a good resonance. We're not trying to draw resonance. We're just trying to show its donating effect. If it donated electrons in, what happens to the pi bond? Where would it move? So we would be generating what charge at that position? A negative charge. If we continue to do resonance, we should notice that we get negative charge at both the ortho positions and the para position. Okay. That means this ring is activated because in the EAS mechanism, our aromatic ring must act as a nucleophile. It has to have electron density. Okay. Because there's still two rings at play, before we start doing anything with it, the left ring, we have to look at the right ring. So move to the right ring. What is the atom on the right ring? Again, another carbon. Okay. Is that donating or withdrawing? How do you know it's withdrawn? You have resonance with the oxygen, generating a fairly large partial positive on our carbon, which means this is an electron withdrawing structure. We can show resonance from the ring going out, which means what charge builds on that first carbon of our ring in the ortho position? Positive charge. And that will likewise build at the other ortho and our last para position. That ring would then be deactivated. Now that we've got enough information on this, we can start to do some evaluations. Our very first bromination should happen on which ring? The activated one, because it is activated. It wants to react faster. It has more electron density. So I need to put my first bromine on that left ring. At what position? The para position, or para, I'll accept it, is more active than our ortho positions because there is some significant steric hindrance from the rest of that structure. Okay, we can rotate about that sigma bond, blocking both ortho positions, at least initially. Okay. Whoops, wrong eraser. I then made it a little bit more difficult because I said you had to do two substitutions. Where should the second substitution happen? Our leftmost ring, what atom do we have as our X? It's a little bit tricky. There's two atom X's. What can you tell me about those atom X's? Okay, the relationship we've discussed so far is what? To hydrogen. Does bromine have more electrons than hydrogen? Yeah. Does carbon still have more electrons than hydrogen? What does that mean the leftmost ring is? It is still activated. The right ring we didn't do anything to. Anybody have any problem saying right ring? It is echoing really weird in my head. Our left ring, is activated. The other one is deactivated. Where should our second bromination occur, left or right?
Right.
Still the left. It is still the one that is activated. The one on the right is deactivated. Stop trying to get me to say those two words. Okay. We now run to the question of where do we do the substitution? Okay. That is a trickier question. Okay. In this case, we will end up doing, please don't lose connection. We will do our substitution ortho to the carbon. And we'll talk about why in a little bit. Okay. So we would expect two substitutions to happen on the leftmost ring. Nothing should happen on the rightmost ring. Okay.
So would there not be a beta substitution or what is it?
Alpha halogenation?
Yeah.
Is that what you're talking about?
Yeah.
It's a good question, which is probably why typically this question is asked as one substitution, not a di substitution, because you'll probably start to see that alpha halogenation come into this. Why would it not do what both? Oh, what am I trying to do? Yeah, I'm trying to draw in here. Putting another bromine there. That would be a third substitution, number 1. So all I said was do 2 substitutions. Okay. Between which of those would it substitute? Both of them are identical. Okay. If we'd have the structure drawn in this fashion, the one I drew is the better of those 2 options because steric hindrance kind of blocks the other angle. You still officially get free rotation there, but as soon as you free up one side, the other side's blocked. As soon as you block one side, the other one's free. So you end up with the same answer either way. Okay? So I want you to remember this. Why did that second bromine go ortho to the carbon? Because we will come back to that in a little bit, and if I don't come back to it, then you can yell at me later about it. Okay? But we want to go in a little bit further before we come back to that. Other questions? Okay. Alkylation versus acylation. Your alkylation requires an active nucleophile. And this is coming from the stability of, the carbocation electrophile being generated. Okay? You need to have an active nucleophile. Your most carbocations, typically the ones you're using, tend to be primary. You're usually using methyl carbocations. Those are not particularly stable, so have a very short lifetime in solution, which means we need something to kind of swoop in and grab it as quickly as possible. So it needs to be an active nucleophile. Acylations, on the other hand, we don't care about. And the reason we don't care about acylations requiring an active nucleophile is because, I don't know why. Yeah. If we look at our active electrophilic structure, this guy down there, that carbon is your active electrophile that has resonance stabilization, which means I can form a sizable concentration of the acylium ion, which is spelled with a C for those of you that were spelling it as a double S on the quiz. Okay. Your acylium ion is resonance stabilized, which allows it to have a reasonable lifetime, which means we don't need as active a nucleophile. Okay. So the acylations tend to happen or be used more frequently than the alkylations for that reason. One thing that might pop up out of this is that if we went through and did an acylation, we wouldn't have just an alkyl group, right? We'd have that stupid carbonyl that carbonyl there as well. So, well, but I don't want a carbonyl. If I want just a carbon chain, why should I bother to do the acylation? Okay, well, it's because the acylation will get you a higher yield, okay, and I can still convert it to the alkylation product. How would I convert it to the alkylation product? I can add a reducing agent like do zinc, tin, shouldn't have done a capital N there. I yell at people for that. Tin or iron in the presence of HCl. Okay. All of those will reduce that carbonyl down to the alkane, and you have the exact same results as if you did the alkylation. Okay. If not better than the alkylation, because the alkylation likely would have rearranged. Okay. So the acylation ends up being the best method to go through and put on carbon structures. Okay. Whoops, went stepwise through this one. The other thing that's interesting is that if we started with an active amine, like aniline, Friedel-Crafts alkylations become very, very problematic. Okay, we might say, well, the amine acts as an activating group. So I should be able to go through and do an alkylation reaction. Okay, if we just added our CH3Cl. Okay, I should be able to go through and do this because that ring is activated. But remember, under Friedel-Crafts alkylation, you need to add the Lewis acid catalyst. And what do nitrogens do very well? Act as both Bronsted bases and really good nucleophiles or Lewis bases. It reacts with the aluminum chloride initiator, which then forms this fancy little complex. If we now look at atom X, what is atom X? A deactivator. Now it won't work under alkylation conditions. What if I switched it up and did acylation? Where would I expect my acylation product to go? So if we clean this all up a little bit. Said, okay, fine, I can't alkylate, let me acylate. Where would I expect my product, or what would I expect my product to be? And we'll say we even cleave off the aluminum chloride later. Where should I put the acyl group? Why are you saying para? Unfortunately, you're wrong, just so you know, but why are you saying para? Okay. You look at it and say, well, your nitrogen is a good activator. I agree. We look at our initial setup. Nitrogen is a strong activator. We would expect para-ortho substitution. We'd expect the para product. We don't see the para product. What product do we end up seeing?
Meta.
We see the meta product. Why do we see the meta product?
I feel like
What happens in the very first step?
deactivates.
It coordinates. Whoops, actually, I think I can just erase that. Not with that button. Coordinates to make that structure, which then means atom X's deactivating group. We'd expect the acyl group to go to the meta position. How was that discovered? Probably by accident. Someone trying to go through and do a para substitution and got a meta product and said that shouldn't have happened. Nitrogens are tricky. Watch out for them. How else did we say nitrogens could react? As bases. Do we have a particular reaction, an EAS reaction that involves strong acids?
Yeah.
We could do a nitration reaction, which was nitric acid and H2SO4. This is a common trap. What might we predict to be our product?
That's
Sorry,
gonna-
there's something in my throat. Atom X in this case looks like
It's going to be picking up a hydrogen.
atom X looks like an activator, so we might predict the para product, and instead we end up with the the meta product. Why? It picks up a hydrogen to generate NH3 plus. Atom X now is a deactivator. When we actually do the nitration, we end up dumping the nitro at the meta position. Okay? So you have to watch out for those kind of sneaky side chemistries. Almost all of them center on nitrogen because it's just an SOB. Okay? Questions? Now that I think about it, I put that on the next one? I didn't. Okay, back to the Friedel-Crafts. Alkylation versus acylation. What product do we expect for this reaction? Okay, number one, should we expect it to go forwards? Yes. If we take a look, we have atom X. Atom X does have extra electrons, is not nucleophilic or as nucleophilic as our nitrogen, so we don't have to worry about that aluminum chloride dealey-bop with the Lewis acid-based stuff. What might we expect for our product? As a hint, all of this is still valid. You want the CH3 at the para position. I'm attempting to agree with you. Okay, we have a slight issue with this, though. What's that slight issue? We now have two activating groups. Which of these two rings should react first, the left one or the right one?
Oh no.
The right one. It is doubly activated. So as soon as we put a single methyl group onto our ring, it is now more active than our initial starting material. Which means, more than likely, we're going to go through and do the reaction again. Okay. And we're going to again encounter that issue that I believe Gina first asked about. We'll put on a second CH3 and it'll go ortho to our oxygen. Now, which of these rings is most active? Again, the furthest to the right. So what ends up happening? It ends up reacting yet a third time. And we'd have a whole bunch of CH3s on our initial structure because it was more active. What does this mean happens to our yield? It's going to be pretty crappy because we're going to get a mix of all three products. We'd have to go through and add a vast excess of that alkyl halide to ensure that it maximized out all the way to the fully substituted product. Okay. So unless we specify that we're adding a vast excess to force that to occur, you're going to get a mix of all three products. Your yield's going to go through the floor. Yes?
So why did the CH3 get added to the orthogonal oxygen?
We'll again come back to that. I keep thinking it's the next slide. That's why I keep walking back and hoping to see it there. It's not quite there yet. So we've got yet another case of this weird oddball thing happening. But we will come back to it, I promise. Okay.
I know you can keep going with the last two positions. You got that one CH3.
Where does so let's just focus on our primary atom X, and we'll address why it's our primary atom X. That is our primary group, which is what's going to force the directing effects. So when we looked at this, we put we went para and ortho to that oxygen, and we'll talk about why we're doing it to the oxygen in a second. But if we look at that oxygen is going to direct the para and ortho positions. At the para and ortho positions, are there any more hydrogens? No, so it can't do any more substitution. The last two positions are meta to the oxygen. They aren't activated. They aren't going to allow for more substitution. The methyl is not going to do enough to overcome the oxygen. Okay. So how could we dodge this? If I want only that first substitution product, how can I ensure that I get just that product? What was that?
You have to remove the CH3.
No.
You make the you make the
Oxygen separate.
Let's make it potentially a little bit easier if we switch that from a CH3Cl to, let's make it a CH3CH2Cl. See if that helps you out. Whoops. These are now all CH2, CH3s. How can I do it now?
Couldn't you just acylate it and then reduce it?
What we just talked about, you can acylate instead. So our reaction could instead be our acyl chloride with aluminum trichloride. That will take us to our monosubstituted again at our para position. Okay. Which ring should react first, our bottom or our top? I know it's a little bit weird. I'm calling this one the top and this one the bottom now. Why the top one? It has an activator on it, and when we look at the bottom one, there is an activator and a deactivator. So as soon as we do that first substitution, we've slowed this product's ability to react. It should not go through and do polysubstitution. Okay. which means I can run my standard conditions, get that single substitution, and then I can follow that up with the textbook seems to like the iron, so we'll stick with that. Our iron and acid, and that will take us to that mono-substituted product. Okay? Kind of makes sense? So watch out with your Friedel-Crafts alkylations. They can kind of mess with you a little bit. So that's that polysubstitution issue. Yeah. Questions on that? Last thing I want to address, I know, I keep saying it's on the next slide, it's on the next slide. But this time I promise it's on the next slide. Okay. But before we get to it, we want to address one more thing, what I like to refer to as our WAs, our WANs, our weird aromatic halogens. Let's pick our halogen. Pick any halogen you want. Chlorine. Okay, I want to pick bromine. Sorry. Okay, all of those halogens. So if we look at bromine, what does it have? Electrons. Okay, so does that mean it has more electrons or less electrons than hydrogen? It has more electrons because it actually has lone pair electrons on it. So because it has more electrons than hydrogen, we would expect it to share those electrons with the ring, which would mean we would expect we have an activator that is para-ortho directing. Okay. Does anybody have any problems with our halogens donating or sharing electrons when they already are sharing electrons? Yeah, we probably have an issue with that. Our halogens, we've grown used to forming one bond and one bond alone. Okay, so there's no way they could share a second pair of electrons. Okay. We add further on top of that, there's no way they could share a second pair of electrons because they are one of our more electronegative elements, which means by definition they should be doing what to the electrons? Stealing them from the ring and pulling them outwards. Well, if they are pulling them outwards, then our halogen should act as deactivators and meta directors. Okay, well, which is it? Why not both? Your halogens will act as deactivators. They will slow a reaction down, but they will still direct the para and ortho positions. Okay? And you may be like, well, that sucks. I don't have to deal with memorizing it. It's the only one you have to memorize. If atom X has more electrons than hydrogen and it's not a halogen, it's an activator, para-ortho directing. If atom X has less electrons than hydrogen, it is a deactivator and meta-directing. If it is a halogen, it deactivates and it goes para-ortho. The halogens are just weird. They do both. Everything else categorizes very, very nicely into either a deactivator or an activator. If it's an activator, it's para-ortho. It's a deactivator, it's meta-director. The halogens, to me, are the only ones you actually have to memorize or spend some time on. How do we know that this is what's going on? Experiment. There really is no other answer, which means ultimately it's a memorization thing. You have to have it memorized. Okay? Questions on that? What's that? It is more of a deactivator than an activator, but it still directs to the para and ortho positions.
Why? Just because?
The hand-wavy argument that you can come up with is that it has lone pairs and an sp3 hybrid orbital that kind of overlaps with the pi system. Because those electrons overlap with the pi system, it builds slightly more electron density at the para and ortho positions. Is it pleasant? Absolutely not. Is that one reasonable explanation for what's happening? Yeah. It works. You may not like it, but it works. Okay. So, multiple substituents. And actually, before we even look at those, we had a couple others that popped up. Remember we had that, see all that junk, et cetera, et cetera? And we said our first substitution happened where?
Para.
The para position. Where did the second substitution happen?
Ortho.
Told you it happened at the ortho. Okay. And ortho to what? To the carbon. It was all in reference to the carbon. Which is weird because at that second substitution, we had two groups. We had the carbon and we had the bromine. Okay. Carbon directs where? Para-ortho. Bromine directs where?
Para. Ortho.
Para-ortho. Where's para-ortho to the carbon?
No. Yeah.
Where's para-ortho to the bromine?
That'd be 2.
So for some reason, when we do this substitution, the carbon gets to direct, not the bromine. Why does the carbon direct? It has to do with the activating ability. The carbon will direct because carbon is a better activator than bromine. Well, bromine's a halogen, which we just said was a deactivator. Carbon is, by definition, almost always activator. So carbon is our stronger activator. It gets to decide where the electron density goes. Okay. If we move to, what was the other example we had? Oh, this one. We have the oxygen and we have our carbon. Where should the carbon direct?
2.
The ortho and para positions. The ortho positions are the only thing available to it. The oxygen directs to ortho para, and again, we see it direct to its ortho positions. The result, if you remember, it went, ortho to the oxygen. Okay. Well, as Amadia suggested in that last question, we look at the activating ability. Well, bromine was a deactivator, carbon was an activator. That was pretty clean cut. If we take a look at this, oxygen versus carbon. Oxygen is activator. Carbon is activator. They're both activators. It's not as clean cut. Why is oxygen a better activator than carbon? It has the lone pair to actually donate through resonance. That is why it is a better activator. Okay? So our directing effect happens based off of our activators primarily. Then it goes based on whichever is the strongest activator. Okay? So let's take a look using that information for the two questions there. And I don't remember if I edited this after I posted them or before. I edited it after I posted it, sorry. I decided to rotate that nitro to a different position. Where would I, or what would I expect for the product? Whoops, it's not a bromine, was it? Okay, identify each. Atom X, in this case, carbon, directs where? Atom X directs.
It doesn't. It's positive.
This is a deactivator versus an activator. So we can actually cheat, and we could just immediately say, well, I'm not going to worry about the deactivator. It's going to be dependent on the activator. Okay? Which works out pretty nicely in this case. So we have 3 positions to do our substitution. Where do you want to dump it? So we're suggesting down here. What do you mean actually no?
Oh, no,
What are
I
you
was-
having a problem with?
I was just thinking of maybe less steric hindrance at that, I don't know if you want to call it number 2 position.
Why do we favor the para position over ortho in general? Steric hindrance. That's why we go to the para. Okay. If we compare these three positions, that para versus our purple ortho versus our blue ortho. Okay. Do they all have steric hindrance? Yes. They are all ortho 2A group, which can sterically hinder. Okay, so now the question becomes, which of those is more likely than any of the others?
Blue,
Why blue?
because it's not in between the two.
The purple one is immediately between two groups. That is two things that are sterically hindering that position. I would say that's a really bad option.
And the red is bigger than, or
And then the red, I would argue that you have a lot bigger atoms with your nitrogen and oxygen than you have with your carbon and hydrogen. You're looking at a larger steric hindrance from the nitro. You should put your bromine at what I've got labeled as the blue position. Kind of makes sense? How about the next one? Or sorry, are there questions about that one before we move on? Okay. Next one. Our atom X in red is activator. Atom X in blue is activator. So I don't have a quick cheat on this.
oxygen has the lone pair, so it's better.
Where, fair enough. Yeah, fair enough. I'll accept that. Instead of even looking at where we could possibly do substitutions, because you'll find that we can do them at pretty much any place on the ring, we should actually rank the activity of these two. Which one is the better activator? Oxygen, because it has the lone pair electrons, which it can donate in, better than the carbon, which makes it the stronger activator, which means I would expect my substitution to happen at the ortho positions to the oxygen. And I would expect my what group? I'm not adding a carbon here. What group am I adding? The nitro NO2 to go to my ortho position. Why did I pick the one on the right, not the one on the left?
They're the same.
I'm right-handed and the one on the right was closer. Okay, they are chemically identical. Make sense? Any questions? Okay, I'm going to do one more curveball here. And I'm going to get rid of that catalyst because that's going to mess with this.
Would you just have that one?
Oops, I should have just erased everything.
Wouldn't you go to both of those parts, or one position?
In that case, you would only get one substitution for sure, okay? For a couple reasons. One, you've got steric hindrance popping up, and two, what was the reagent or functional group that you were putting on? A nitro. And what is a nitro?
Yeah.
A strong deactivator. As soon as you put on a single nitro, pretty much the whole ring is deactivated. Your substitution patterns will still be based off of your activator, but the ring is now pretty much shot. Okay. Which is why to make TNT, try nitro-toluene. To get 3 of them on there, you have to use increasingly more strenuous circumstances. The first nitro, well, we'll just talk about it. You'll typically start, or one way to start is with toluene. The first one you can usually get put on with just concentrated nitric acid, also known as fuming. Okay. And that would likely go to your para position. Whoops, I don't know why I was drawing a carbon. If you left it with fuming nitric acid, it's not going to do much. Okay? It's just going to sit there and look at you pathetically. But if we go through and now up it to nitric acid and sulfuric acid, you can probably get that second one on there. But now you're kind of SOL. To get that third one on, your stiffest conditions, at least that you guys are aware of, is nitric acid and sulfuric acid. You don't have any stronger acids to help initiate and push that along. You're probably going to stall here. And with 2 nitros on there, that ring is now massively deactivated. It has virtually no electron density. Okay? So the likelihood of getting that third one on now kind of falls off until you bring in a lot of extra conditions, potentially stronger acids, a better nitro provider, or nitronium ion source, or really stupidly high heat, which generally not a good idea with an explosive. Just thoughts. Okay. So back to the question I was going to jump on here. And any guesses what I'm going to draw down below? Is the other substituent going to be? Nitrogen. Where do we expect the bromination to occur?
I would say ortho to the nitrogen.
So I heard ortho to the nitrogen. Anybody want to second that? Disagree with it? You shouldn't disagree with it. Goes ortho to the nitrogen. Why?
It's a better.
If oxygen was a better activator, we would expect it closer. We would expect it at the ortho position to the oxygen. So oxygen is not the better activator. It is ortho to the nitrogen.
Nitrogen
Okay.
carries a positive charge better.
Nope. What's that?
Nitrogen is more willing to share electrons.
Nitrogen is less electronegative than the oxygen, which means it is more willing to share electrons.
That's why I said that.
Oh, what I heard.
It carries the positive charge better.
I see where you're going with that now.
I mean,
Yeah, I
it's
could see
not
that
a
potentially
good
work.
positive, but
I could
still
see where you're
better
going with
than
that, within one of your resonance. The nitrogen donates electron density better than the oxygen, which means the nitrogen is now your stronger activator than the oxygen. This is a common question because most students, which, good job you guys didn't do it, look at the oxygen and say, well, there's 2 lone pairs. It has more electrons, so it can donate more electrons. How many electrons can it donate at any given instant? 2, and only 2. The other pair of electrons are located where? In a perpendicular orbital that cannot contribute to the pi system. So we can only get, at any point, contribute 1 pair of electrons. Okay? Which means the sheer fact that oxygen has more electrons is irrelevant. Okay? So we have to move to another idea. That's where we see the difference in electronegativity.
So in a lot of the previous examples, the oxygen was still a better activator because those had no electrons to give.
Exactly
And
right.
when there's electrons to give, you look at which one's less electronegative.
Yes, exactly right. Okay. Other questions? Okay, good job. Does that now get back to, now Princess and Gina both asked the same question at different points earlier, to the directing effects? You guys okay with that now? So I believe I've got it summarized down here. If you have multiple substituents, your activator trumps your deactivator, stronger activator trumps weaker, which really is just one lesson. The stronger activator trumps everything. Okay, that's by definition the activator is stronger than the deactivator, right? Okay.
Is there any way you would have a deactivator that's stronger than any of the activators?
No. Could you have a deactivator that's stronger than another deactivator? Yes. Okay. Which product or what products would we expect in higher yields? So hopefully you'd recognize that we could nitrate both of these, and we just kind of ask these same questions. Which of these two products do we expect in the higher yield?
The one on the right.
So based on activator, deactivator, what are we comparing? Carbon to carbon. Is there a difference in activating strength there? None. So we can't use this activator ability to decide where our nitro group should go. So what should we use? The steric argument. So using sterics, we would expect that our nitro group should go ortho to the methyl group instead of the, oh, you guys did get it, isopropyl group. Good job. Or whoever said that.
With the isopropyl, you wouldn't have more donating ability going in?
There's not enough electron donating capabilities within that to get anything significant happening there. And the next one down. Okay. And you'll notice that there's a third product that is not drawn. So let's real quickly draw that third product. You can probably already tell me why that one wouldn't exist. I guess they showed it in red. I should show it in red. Between those three products, which is the most likely? Okay. Yeah, that is left, isn't it? Your bottom left is likely the best. The top one, the least likely, because you've got sterics on both sides, making that a bad option. The bottom right has more sterics than the bottom left. Okay? So it's kind of a piece together process and putting it together and figuring out how to go. Questions about that? Okay. I'm just curious where we are, about 10 slides out. Steric directing effects and reversibility. So how would you synthesize that product in a reasonably high yield? What's the difference between those two? Yeah. So if all you gotta do is brominate, what should we use as a reagent? How about Br2? Because we have an activating group, we probably don't need the catalyst, but you know, just for giggles, why not? And other things, I guess. Could add our catalyst in there. What product would we expect from this? Para substitution. Oh. Well, maybe we add the catalyst so that I can get it at the ortho position. That'll get me the ortho position also. So if I add under these conditions, I'm probably going to end up with this product. It's not the product I wanted. So, back to the original question. How can I get that to happen?
Some sort of
I need a blocking group. I need to do an EAS reaction that blocks the para position. Now I wonder, was there any of those lists of reagents that we said, this one's a neat reagent because it's reversible? What was it? Adding? No, we don't have any reagents that'll do an OH neatly.
Is it the
Fuming sulfuric acid will do what? A sulfonation. It should go to the para. Whoa, that's an S. Gosh, that was horrible. Which should go to the para position. Why should it go to the para over the ortho? Steric hindrance. Then what can I do? Now I can do the bromination.
You said it's fuming?
Yeah.
Does it have to be?
You might see fuming. Fuming is important for it because you need a really high concentration of sulfuric acid, and we'll talk about why you need a really high concentration in just a second. The sulfur group will likely act as what? A blocking, yeah, it does act as that, and a deactivator, so we will probably need the presence of the catalyst to help get this reaction to go. This gets me the bromine that I wanted on it, but I still have that stupid sulfur group. How can I get rid of the sulfur group? I now need to do the desulfonation. The desulfonation involves now dilute H2SO4, the primary aspect being H2O. Okay. We need the dilute acid because we have to protonate, but water is going to be the driving force to reverse this reaction. Okay. And we'll end up going right back to where we started. Okay. So why does it need to be concentrated to begin with? To the point that it is fuming, because if it's dilute, it undoes it. So we need to have concentrated fuming sulfuric acid to really push the reaction forward to put that sulfate group on there. Okay.
And it's got the hydrogen on it because it's in an acidic environment.
Yeah. Okay. So we've got a steric effect and blocking effects, a little bit of reversibility tossed in there. Kind of a fun little thing to look at. Okay,
And
let's see.
water's not going to be enough to
No. Water is not a strong enough nucleophile to cause the bromine to leave. Getting the bromine to leave in general in a substitution reaction, think back to that lab that we did in first semester with bromobenzene. Did it react under SN1 or SN2 conditions? It did not. The only way to get that bromine to leave is going through the NAS mechanism, which is our last 10 slides. Okay. So what I kind of want you guys to do now, let's take a look at this last reagent here. I want you to synthesize this starting with benzene. And that is what we will end with today. Starting with benzene, go through and do this reaction. Okay. As a quick, potentially helpful hint on why I like EAS reactions. How do we put on the nitro? What was that? Not NH2. How do you get on the nitronium ion? HNO3 and H2SO4. Try and screw this up. Yep. How do we get the bromine on? I'm going to say Br2. Kind of boring on that one. How do we get the acylium? Do that right? 3 carbons? 1, 2, 3. Yep. That's our Friedel-Crafts with our AlCl3. Okay. So EAS is nice. I would kind of classify it as almost like baby synthesis because there's only so many reagents that you can use, but the order becomes of critical importance. So you guys should be able to memorize the reagents pretty quickly, and then it's a question of, okay, what order do my reagents go in? Particularly in a multiple choice exam, you're given the reagents. You just have to say, it's going to give me this electrophile. Okay. I am going to stop there. If you've got questions about what that answer